Hello, and welcome to my talk on visualization transforms of non-spatial data for convolutional neural networks, or CNNs. I'm Suhas, and I work for Wells Fargo, although none of this work was conducted as part of Wells Fargo. I also run a social impact nonprofit group that we recently started called L'Une. Please feel free to check out the website, which is going to be a part of these slides at the very end. And so the pandemic got me thinking, and I really got bored of slides. So today we're going to look at something a little different. Hopefully it's going to be more interactive, more interesting. And okay, so here we go. The central theme of this talk is, can we bring in the power of convolutional neural networks to various machine learning problems on tabular datasets? By tabular, I mean the ones, okay, this is a glitch. Okay, by tabular, I mean a dataset that looks like this, where you have a bunch of observation vectors and some features. And let me rewrite this so that it's clear. So each row is an observation vector. And let's assume that we have n such rows. And each column is a feature, or maybe you want to call it a predictor, but each column is a feature. And then you have m such features. And then let's assume this is a supervised classification problem, just so the notation and the discussion is easy, but rest assured that everything that we're going to talk about today is equally applicable to unsupervised problems and regression problems as well. Okay, this is x, that's the input, that's y. And traditionally for tabular datasets like these, the most popular algorithms of choice are random forest, XGBoost, gradient boosting, sometimes support vector machines. And CNNs are extremely good at mimicking the human visual system. But for problems, in my personal experience and also literature tells you that the problems that are not necessarily expressed as images are not greatly benefited by using CNNs. And in order to bring the world of CNNs to these tabular datasets, so why are these important? Because these have applications in a variety of interesting areas, okay? Interesting and useful. Applications in, finance and healthcare and pharma. So you find a lot of these tabular data sets. And the goal of the problem we're trying to solve is very simple. So we have the labels y and the input x, right? We want to find, okay, so we want to find a function f such that y equals f of x. So far, so good. However, when x turns out to be a tabular data set, like I said, CNNs are not particularly useful. I mean, they're not bad, but you're not using the full power. So instead, what we want to do is come up with transforms and which convert a tabular data set x to an image z. Okay. So I'm just going to write this as a matrix, and this is an image. Oops. Oh. I'm having a technology glitch. Okay. And now, when we write y equals f of z, where z is an image, it would make much more sense for y to be a CNN model. So that's the primary goal. Now, before I move on, I just want to focus a little as an advertisement for the rest of the talk that it turns out that Um, so we are looking at mainly three different data sets in this presentation. The first two are simulated. The third one is an arrythmia data set. It's a real data set that was part of a study conducted by MIT and Beth Israel Hospital in Boston. And in all of those data sets, this is a classification error. The least classification error was given by CNN algorithms that were trained on the images that we generate from these tabular data sets. As opposed to what? As opposed to random forest and a fully connected neural network that were trained directly on the tabular data set. So what I'm trying to say is when you convert it into an image, we do much better in terms of classification error. And in order to do that, we're going to look at two different transforms. The first is a vector to image transform, which takes every single observation vector in our data set and then converts it directly to an image that looks like this. Okay, and then the second transform is one where we look at the observation vector, and instead of directly converting it to an image, we modulate a noise vector, and then using this observation vector, and then we feed that noise vector into a trained GAN. In this case, our GAN was trained on the MNIST dataset, which is why you see all these digits, but it really could be anything. It could be like images of animals or cars or dogs, waterfalls, you name it, okay? So you get the point. But so we take an observation vector, convert it into a code, and then use that code to modulate the noise vector for a GAN, and from the GAN we produce an image that looks like this. So there are really two routes for going from an observation vector into an image, and then we're going to look at both. Okay, so the first one is VTI, which stands for vector to image. That's the direct transform. And the idea is really simple. Let's say we have one observation vector. This is a 1 cross m vector. And so, well, there are m feature values, right? And let's say the first feature is alpha 0, next is alpha 1, dot, 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 alpha m minus 1. And let's say there are values like 6, 7, dot, 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 4.5. So how do we convert such a row of numeric values into an image? One obvious way is to write each of these values, 6, 7, dot, 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 4.5, as individual pixel values and just call it an image, okay? So that's just reshaping. And we're going to see that's not very helpful because we're finally going to get an image that's extremely small. And the number of pixels in such an image would be equal to m, which is the number of features. And okay, don't be surprised in a lot of healthcare and finance datasets if this m is significantly small. So what I mean is m could possibly be something like, okay, 15, you might have 15 variables or 15 predictors, or you might have 100, or you might have like 1,000. 1,000 is a very big data set in finance, for example. And so if you have 1,000 pixels in an image, it's really not a very large image, and we might run into problems when we're using CNN. So, okay, that's one problem. The other problem is each of these features has a feature importance. Let's just call it W0, W1, all the way to W m minus 1. So the W's are the feature importance, and by making one pixel out of every single feature value, what we're failing to do is allocate more image area to those features that are actually more important than other features. So, okay, so in order to fix both of these problems, we're just going to assume that our image has p squared pixels, okay? So p squared pixels in our final image, transformed image z, and so we allocate n sub I pixels to each feature, okay? To each feature alpha I, and this is how we're going to compute it. N sub I equals the feature importance value W sub I times p squared, which is the number of pixels, and then we're going to normalize this um, like this, okay, by summation of all the, okay, uh, let's, the easiest way to write this is j equals 1 to n minus 1. And, okay, so we're assigning n sub I pixels to feature alpha sub I. So, and then we do a bunch of other things. For instance, okay, we form an image, right? Okay, we form an image that looks like this. And let's say these are all the, so that's for alpha 0, and maybe that's for alpha 1. And these are the pixels for alpha 2, and so on, right? And that's for alpha 4 and so on. And now what we do to capture feature interactions, we apply a Gaussian on top of this, okay? So on top of this image, we apply a Gaussian kernel. And that's going to smooth the pixels over, and the smearing of those pixel values is a representation of characterizing the dependence of different features upon each other. For more information, there is plenty of detail in the paper, so I'd encourage you to look at that. And the second transform that we're going to talk about is the VTC, or the vector to code. The idea is, again, fairly straightforward. The first, okay, so step number 1 is, okay, let's assume we have a noise vector that's the same length as, okay, so that's a 1 cross m vector. So that's the same length as our observation vectors. And then we modulate the noise vector, or equivalently, we call this a latent code. And let's say this is U, and we modulate to get U tilde, and then we pass that through again, and then we get our final image Z. So that's our transformed image. And the modulation task is where the xi, which is the ith observation, comes in. So the ith observation is used for modulation, and then we get an image Z sub I, which is the corresponding image. The paper has plenty more details about the way we modulate, but the general idea is that, so if U is a random, okay, let's say it's a noise vector that's a 1 cross m, and U tilde, after modulation, has the form that looks like this. So A sub theta of U plus lambda x sub I. So where lambda is a diagonal matrix, and in our case, this diagonal matrix looks like, okay, let me write it down for clarity. So you have lambda 0, lambda 1, all the way to lambda n minus 1. And each of these is actually, in our case, lambda sub I equals wi, which is the feature importance value. And the rest are zeros. So this is a diagonal matrix. And then A sub theta is a rotation matrix that's given, okay, it's the easiest way to rotate these vectors, noise vectors U, is through a quaternion notation. So we only choose the top 3 variables in this paper and rotate those the corresponding elements of those top 3 features in the noise vector. So the way we do that is if we have a quaternion that looks, okay, let's say it has the form a to the, okay, theta divided by 2 times bi plus cj plus dk, where I, j, and k are unit vectors in the Euclidean space. So, a mapping of the form. Okay, so if x is the observation vector and q is the quaternion, it's a pure quaternion, and then qx, q inverse would represent a rotation by an angle of theta. And so in our paper, we use this notation and this procedure for convenience. But in any case, this is the central idea of vector to code transforms, where we take in a noise vector, we modulate it with this formula here. This is the modulation formula, where we first rotate the top 3 important elements of the noise vector that correspond to the most important features of x, and then we add the corresponding values of x based on a weighting scheme that's given by a diagonal matrix. Okay, so once we have a code and then we feed it into again and we get an image, this is what it looks like. This is the time to look at some results and see what's happening. So the first 2 examples we see are, okay, let's say there are 2 observations that look like this, 1.4, 0.8, 7.4, and x. Okay, so let's say we have a data set with 2 classes, the 0 class and the 1 class, and x0 is a member of class 0, and x1 is a member of class 1, and let's say the actual vectors look something like this. And their corresponding VTI images look like this, okay? And where you see, okay, x0 is the 0 class and x1 is the 1 class, and you see sharper delineation between different regions of the images here. So just by visual inspection, it's possible to say, okay, that belongs to that particular class. And the VTC examples are given below here. So for the positive class or the 1 class, you see proper digits, but however, for the 0 class, you see weird kind of digits which actually don't make sense. This is a distorted version of either 5 or it could be like, I don't know, an 8 that's not complete. But visually, you do make out the difference between class 0 and class 1 after we've done the VTC transformation. The last example I want to show is the examples are actually illustrated well in the paper, but this is the MIT the Beth Israel Hospital dataset for arrhythmia. So these are 5 different types of heartbeats, and the first one is normal. So this is the normal heartbeat, and everything else is some kind of abnormality. And again, so the normal heartbeat for the VTI transform, you see, has a particular signature or a pattern in the images, and all the other images look a little different. So just by looking at the images, you can tell one heartbeat from another. And the same for the VTC transformed images, where all the normal images are typically represented by 0 in the MNIST dataset, and the abnormal images cycle through different digits. And yep, that is the gist of what we're trying to do here, where we're converting a tabular data form into images so that we can fully harness the power of convolutional neural networks. And it's truly exciting. I appreciate your comments, feedback, questions. Please reach out to me. My email information is in the paper. Thank you for your attention and stay safe.